Assalamualaikum. My name is Muhammad Ridhuan bin Yusuf, and today I would like to talk about radio frequency propagation. Radio propagation is the behavior of radio waves as they are traveled or are propagated from one place to another or into various parts of the atmosphere. Radio waves, like light waves, are influenced by reflection, refraction, diffraction, absorption, and scattering as a form of electromagnetic radiation. There are several types of propagation that are used in practical radio transmission system. First is the line of sight. Line of sight means a radio travels in a straight line from the transmitting antenna to the receiving antenna. Line of sight transmission is used for medium distance radio transmission such as cell phone, cordless phone, walkie-talkies, wireless networks, and more. The line of sight will not be smooth if there occurs any obstacle in the transmission path. Secondly is non-line of sight. For non-line of sight, it occurs outside the typical line of sight between the transmitter and receiver, such as in ground reflection. Non-line of sight conditions refers to partial obstruction by a physical object present in the innermost Fresnel zone. Obstacle that commonly causes NLOS propagation includes building, trees, hills, mountains, and in some cases, high voltage electrical power lines. Our objective for this assignment is to investigate outdoor radio frequency propagation by conducting an outdoor site survey. Secondly is to compare the measurement or the result that we have gathered with the outdoor propagation model. Next, my partner will explain the methodology.
Okay. Hello, my name is Saifullah, and I'm going to talk about methodology. So, how do we do this project is we take an TP-Link outdoor CPE, CPE 220 and 510 to imitate the base station. CPE 220 transmitting 2.4 GHz, while CPE 550 transmitting 5 GHz. Each of these have their antenna gain, which 2.4 have a 12 dB antenna gain, while 5 GHz use 13 dB antenna gain. This is due to the fact that each of these have similar behavior for radio wave antennas. So we placed it at the 4th floor near the elevator, as seen as the picture. For the transmitter, we purposely tilt the transmitter downward with 45-degree angle to face the ground, so we can read the readings better, so there is minimum losses. And we use a software called Insider for it to take the readings of the signal. We use our laptop as a receiver for both 2.4 GHz and 5 GHz. We begin the reading as soon as we saw the antenna above, and we started from there. We continuously use the same process as we step away from the antenna, which is 1 meter each step. So as seen as the picture, we estimately the height of the antenna is 12 meters, and as we progress moving distance away, we move 1 meter away, and the map shows the route we took to get the readings. Until we get to the side of the building, we take the reading as a non-line of sight readings.
So for the outdoor propagation model comparison, I have chosen the free space propagation model. So what is free space propagation model? So basically, this model is used to predict received signal strength when the transmitter and receiver have a clear, unobstructed line of sight path between them. So without further ado, I will show the calculation of the free space propagation model. Okay, so the formula for free space model is, hold on, I write it. So the formula is PRT PT GT GR lambda square for 4 pi squared D squared L. So PR means power receiver, so PT is transmitter power, GT GR is the antenna gain for transmitter and receiver, lambda is the wavelength, for pi D squared is the distance. So the first distance that we are using is 20 meter. For the PT is the 500 milliwatt. So the first distance is 20 meter. For PT is 500 milliwatt. So 500 milliwatt is the equipment that we have used. So first is 500 milliwatt. GTGR is 1. Lambda squared is FC. S is 3 times 10 to the power of 8. So C is the carrier frequency is 2.4 gigahertz. So we get 0.125. So at lambda we put it here, 0.125 squared. So 4 pi squared, distance is 20 meter squared. Okay, so zero point 125 squared. So we get 1.237 times 10. So we want to get in dB. So in order to get in unit dB, we need to 10 log 10. The answer 1.237 times 10 to the power of -7. 10 log 10. 1.237 to 7. Oops. We will get negative 69 dB. So for the next distance is 30 meter and 50 meter. So for 30 meter, so hold on, first one, milliwatt. Same number. We change at the distance. We only change at the distance. So 30 meter square. Okay. So we get 5.497 times negative 8. Same sequence to get dB. Then log 10, the answer 7 times 10 negative 8. So we get negative 72 dB. For the last one is 50 meter. So yeah. Oops, sorry. 50 meter. So we get 1.9779 times 10 to the power of 8 to 10 log 10 979 of 8. We get negative 77 dB. Next, we will calculate for the 5 gigahertz. Okay, so for the 5 gigahertz we use the same formula, but apologies for the earlier. For lambda square we use C over F, not F over C. So this will get, for lambda square of 5 gigahertz we will get 0.06. So for the first distance is 10 meter, but we will be using 10 meter. Transmitter power is 200 milliwatt. Okay, so we will put it here. PT is 200 milliwatt. GTGR is the same, 1. Lambda square is 0.06 squared, 4 by squared over distance is 10 meter. So we will get 4 over 4.559 of negative 8. So we convert it into dB. 10 log 10 so we'll get negative 73 dB. Next is for the 40 meter and 50 meter. It is the same calculation, so I will skip ahead and show the final result. Okay, so this is the result that we have acquired. So for 10 meter we will get negative 73 dB. For 40 meter we will get negative 85 dB, and for negative 87 dB for 50 meter we will get negative 87 dB. So that is all for the calculation. Next we will calculate for free space for path loss. Okay, so next is we calculate the path loss. So the first path loss we will calculate for the 2.4 gigahertz. So this is the formula that we'll be using. So PL means path loss in dB. So negative 10 log over lambda squared is 0.125 squared over 4 pi squared. Distance is 20 meter squared. So we will get 66 dB. So for the next distance is 30 meter and 50 meter, so I will skip forward again to see the results. Okay, so this is the final answer that we get. For 30 meter we will get 69 dB, and for 50 meter we will get 74 dB. So next we will show the calculation for the 5 gigahertz. Okay, so for 5 gigahertz for lambda is 0.06, and for the distance we'll be using for 10 meter, 40 meter and 50 meter. So we will do for the 10 meter first. 10 meter is negative 10 log, lambda is 0.06 squared, 4 pi squared. The distance is 10 meter. This 10 log 10 to 0.06 squared, 4 pi squared equals 10 squared. So we will get 60 dB. So as usual, I will skip ahead and shows the results later. Okay, so this is the final answer that we get. For 40 meter we will get 72 dB, and for 50 meter we will get 74 dB. As you can see, 40 meter and 50 meter the result is not that far, is 72 and 74. So that is all from me.
For the second propagation model, we use a commonly used propagation model, which is Okumura model. So this is the calculation of Okumura propagation model. Started with the info given, distance of 40 meter, the height of transmitter we assume, which is 20 meter, height of receiver, which is 1 meter, IRP, which is given from the CPE 220, which is 500 milliwatt, and with a frequency carrier of 2.4 gigahertz and a receiver gain of 1 dB. First, using the formula given, first with Okumura we have to calculate the path loss. The free space path loss we calculate, and we have a 57.03. To get the median attenuation we have to refer to the graph. For 2.4 gigahertz attenuation for distance up to 1 kilometer, we get 30 dB from the graph. From the gain of height of transmitter we have negative 10 dB, and the gain from height of receiver we get negative 4.77 dB. And for area gain from Okumura, you have to refer to the correction factor graph from Okumura given in the picture, and referring to the picture with the most suitable type of area using Okumura models, which is suburban area, which is not very narrow but small areas, and we get a 13 dB. After gaining the all information, we place it with the number we have calculate, and the total path loss is 71.8 dB. Finally, we have to convert the EIRP reading 500 milliwatt to dBm, and we get a 27 dBm. And to calculate the median received power, EIRP minus path loss plus receiver's gain, and we get a number for 40 meters readings, which is negative 43.8 dBm.